Section 2.5 Implicit Differentiation. So far, we have been taking derivatives of functions that are written in explicit form. But not all functions can be solved for y. Some functions simply cannot be written in y equals. So now, you're gonna learn how to take the derivative of functions that are written in implicit form. So let's start finding derivatives using implicit differentiation. First, look at the functions that are written in explicit form or implicit form. So you can see the top example of explicit form, and it is y equal 5x cubed minus ln x plus radical x. So you can see how y is isolated on the left, and on the right hand side, your function is all written in terms of x. That's called explicit form. Now that you look at the bottom equation, I have x cubed minus 2y plus 3y squared equals 7x cubed minus sine y. When an equation is written x and y combined together in one side or both sides, and simply you cannot isolate y variable, we say function is written implicitly. So this is implicit form of an equation. And in this section, we're gonna learn how to take implicit differentiation. We can still find dy dx even if function is written in implicit form. So let's do a little practice here. When you take the derivative of x cubed with respect to x, it is explicit since you're just taking derivative of x cubed function in terms of the same variable. And as you know, derivative of this is just 3x squared. Same thing, I just changed the variable, same expression to t. So when you have a function of t, but you are taking derivative with respect to t, it is still explicit. So it is regular derivative, which is 3t squared. However, now if you are taking derivative of the same x cubed, but it is respect to t, then we are assuming this x is a function of t. So it's a function raised to the power 3. So you need to use a chain rule here. By chain rule, you take the derivative of outside the function first, which is 3x squared, and now you take the derivative of x with respect to t. So that's what you multiply by, which is the x prime here. Same thing, if you are taking derivative of y cubed with respect to x, now you're looking at the y as a function. So you're gonna need to use a chain rule here. So this will be 3y squared, but now I need to take the derivative of y respect to x, which is the y prime. So you need to use a chain rule here again. So let's do one more practice. So let's say I'm taking derivative of x squared y to the fourth with respect to x. So x is explicit, y is implicit. Y is a function of x. So you can use the product rule and the quotient rule at the same time. So let's say you have f times g. So when you take the derivative, of course, you want to do f prime times g plus f times g prime. Then f prime, because x squared is explicit, derivative is just 2x times g, we just copy y to the fourth, plus, now f, we just copy, f is x squared times g prime. Do you see how g is y to the fourth, and if you take the derivative of y to the fourth with respect to x, it is now implicit, so therefore we need to use chain rule. So derivative of that will be 4y to the third power, but now you need to take the derivative of this function with respect to x. Get it? So now that will teach you how to take the implicit differentiation. So this is how to use implicit differentiation to find the derivative of a function. First, you differentiate both sides of the equation with respect to x. So then some terms will have a dy dx, some terms will not have a dy dx. So move all the terms having dy dx in one side. I typically move to the left, and move everything else to the other side, meaning terms that do not have dy dx, you move to the right hand side. And now on the left hand side, every term will have a dy dx, so you are going to factor dy dx out from all terms having dy dx. So dy dx sits in the front, and you will have a bracket or parenthesis right next to dy dx, and you can divide both sides by factor right next to dy dx. So now you have dy dx or the y prime. That's how you are going to find dy dx when function is written in implicit form. Let's try now real implicit differentiation problem. Follow the direction. Find dy dx given y to the fourth plus 3y squared plus 2y minus x squared minus x equal 5. So first, you're going to differentiate both sides of the equation with respect to x. So take the derivative of both sides with respect to x. So notice that when you take the derivative of y to the fourth, 3y squared, 2y respect to x, y is a function of x, so you need to use chain rule here. So then it becomes 4y to the third dy dx plus 6y dy dx plus 2 dy dx. And to take the derivative of negative x squared minus x with respect to x, it is explicit, so it will be just negative 2x minus 1 equal derivative of a constant is 0 on the other hand side. Now step 2, move all terms having dy dx in one side and move all other terms on the other side. So we are going to leave the 4y cubed dy dx, 6y dy dx, 2 dy dx on this side, and we are going to send negative 2x and minus 1 to the other hand side. So then I will have 4y cubed dy dx plus 6y dy dx plus 2 dy dx equal 2x plus 1. Now factor dy dx out from all terms having dy dx. So let's factor out dy dx on my left hand side, open bracket, then I will have 4y to the third power plus 6y plus 2 equal 2x plus 1. Now divide both sides by the factor next to dy dx. We're trying to find the dy dx, so you are trying to isolate dy dx. So divide both sides by the 4y to the third plus 6y plus 2, 4y to the third plus 6y plus 2. So these get canceled. And finally, your dy dx is equal to 2x plus 1 over 4y cubed plus 6y plus 2. So you found the derivative of y. Not too hard now that you know how to do it, right? Let's do a little bit more challenging one this time. Find dy dx given x cubed plus y cubed equal square root of xy. So first, differentiate both sides of the equation with respect to x. We will do that. So I have derivative of x cubed plus y cubed with respect to x equal derivative of, I want to rewrite this function. Since it's a square root, let's use power. It becomes quantity xy to the 1/2 power. Since I'm taking derivative of x cubed with respect to x, it is just 3x squared plus, now I'm taking derivative of y cubed with respect to x, that will be implicit. So that will be 3y squared times dy dx, which is equal to, on my right hand side, I have a function raised to a power. So I need to use chain rule here. So when I take the derivative, I need to take the derivative of outside the function first, which is 1/2 whole thing to the, I lose 1 power. So 1/2 subtract 1 is negative 1/2 power. And xy was what was sitting inside. Now I need to multiply by derivative of inside the function, and my inside the function is a product. So I'm gonna call this f times g, and as you know, derivative of f times g is f prime times g plus f times g prime. So you take the derivative of x, we're taking with respect to x, so that will be just 1 times g, you just copy, so it is just y, plus f, you just copy, which is x, times g prime. Now I'm taking derivative of y with respect to x, so y is a function of x again. So derivative of y will be 1, but I need to multiply by dy dx. Step 2, move all terms having dy dx in one side and move all other terms on the other side. So I see that I have a dy dx term, one of them here, and another one right here. But this one I cannot move because it is multiplied by 1/2 and also xy to the negative half a power. So let's rewrite this so that it's easier to see what's going on. I have 3x squared plus 3y squared dy dx equal, this bracket is a numerator, so I have y plus x dy dx over, factor 2 is in the denominator, and this xy to the negative 1/2 power is negative exponent, so when I move to the denominator it becomes positive exponent, but 1/2 power is a square root, so I can change back to square root notation. And because of that 2 radical xy in the denominator, I cannot move x dy dx term from the right to the left. So let's get rid of this denominator term by multiplying both sides by 2 radical xy. So I'm going to multiply both sides by 2 radical xy and 2 radical xy, so that these get canceled. Now I do see that x dy dx can be moved, and this I will distribute so that dy dx term can be separated. So then I will have 6x squared radical xy plus 6y squared square root of xy dy dx equal y plus x dy dx. So I'm going to have dy dx term on the left, and any terms that do not have dy dx, I'm gonna move it to the right hand side. So you will have then 6y squared radical xy dy dx minus x dy dx equal y minus 6x squared radical xy. So now I'm in step 3. I'm gonna factor dy dx out from all terms having dy dx. There's only 2 on the left. So factor out dy dx. It will give me dy dx bracket 6y squared radical xy minus x equal y minus 6x squared radical xy. Step 4, divide both sides by the factor next to dy dx. So I'm going to divide both sides by factor next to dy dx, which is 6y squared radical xy minus x, 6y squared radical xy minus x, so that these can be canceled. Dy dx is equal to y minus 6x squared radical xy over 6y squared radical xy minus x. And this is your dy dx. However, a lot of time we do not wish to have a radicals in our answer. So then, because original problem radical xy was equal to x cubed plus y cubed, you could replace radical xy by x cubed plus y cubed to not to have a radical in your answer. So that will be y minus 6x squared times quantity x cubed plus y cubed over 6y squared quantity x cubed plus y cubed minus x. And if you multiply that out, that will be equal to y minus 6x to the fifth minus 6x squared y to the third over 6y over 6x cubed y squared plus 6y to the fifth minus x. And that is your dy dx. Find the equation of the tangent line at the point 13, 0. So this time we're gonna find the equation of a tangent line, and we know how to do that, right? And we're given a point, like always. And so we need to find the derivative of function, which is dy dx. And we're going to plug 13, 0 there to find the slope at this point. And then once we have the slope, we're going to use point slope form of a line to write the equation of tangent line. And now, since our equation is x plus xy squared plus sine y equal 13, we need to use implicit differentiation. So let's take the derivative both sides with respect to x. That's your first step of implicit differentiation. Equal derivative of 13 with respect to x. So when you take the derivative of x with respect to x, derivative is just 1. Now for that one, x times y squared, to take the derivative, we need to use product rule, right? So you can call this f times g. So derivative will be again f prime times g plus f times g prime. So derivative of x with respect to x is just 1 times g is just y squared plus f is x and g prime. I'm taking derivative of y squared with respect to x. So we need a chain rule here. So that will be 2y times dy dx plus, now you're taking derivative of sine of y with respect to x. So that will be composition of a function again. I need to take the derivative of outside the function, which is a sine function. And derivative of a sine function is cosine of y. And I need to take the derivative of inner function y, which is 1 dy dx, which is equal to derivative of 13 is 0. And then we collect all the terms having dy dx on the left, and then all the terms that do not have dy dx, we send it to the right hand side. And then since we're gonna factor out dy dx afterwards, let me go ahead and do that two-step at the same time if you can follow. So I have dy dx factored out from these two terms. So I'm gonna have 2xy plus cosine y, which is equal to, now I'm gonna move these two terms to the other hand side. So they're gonna go to the right hand side and become negative y squared minus 1. Now to solve for dy dx, what do we need to do? Yes, last step is to divide both sides by factor next to dy dx, which is 2xy plus cosine y. So I found the dy dx. My dy dx is equal to negative y squared minus 1 over 2xy plus cosine of y. So my slope at 13, 0, I just plug x equal 13, y equals 0. Well, this time I do need both x coordinate and y coordinate, as you see. So negative 0 squared minus 1, 2 times 13 times 0 plus cosine of 0. So I have negative 1 over, this is 0, cosine of 0 is 1. So slope is negative 1. So now you have a slope negative 1 and you have a point 13, 0. You can finally write the equation of a line, and your equation of a line is y minus y1 equal m parentheses x minus 13. Well, this one is really simple enough. Let's just give a slope-intercept form of a line. So y equal negative x plus 13 is the equation of a tangent line at 13, 0. Last problem. Find d squared y over dx squared for x squared plus y squared equal 49. Guys, do you remember this? What's d squared y over dx squared? Yes, second derivative. They want you to find the second derivative of y. And to find the second derivative, we need the first derivative first. So let's find the first derivative. Take the derivative both sides with respect to x. So d dx of x squared plus y squared is equal to d dx of 49. Now when you take the derivative of x squared with respect to x, it is just 2x. And when you take the derivative of y squared with respect to x, use chain rule, you get 2y dy dx. Very good. Equal to derivative of 49 is 0. This is very simple, huh? There's only one term that has a dy dx. So you can leave that one there and just send the 2x to the other hand side. So I have 2y dy dx equal negative 2x. Now you can divide both sides by 2y to isolate dy dx. So then even 2's get canceled on the right hand side also. So I found my dy dx. My first derivative is just negative x over y. So now I would like to take the second derivative. So then how do you do that? You take the derivative of a first derivative, right? So d squared y dx squared is you're taking derivative of dy dx with respect to x again. So that will mean that you're taking derivative of what you just found, which is negative x over y with respect to x. But this is a quotient, right? So to take the derivative of that, you need to use quotient rule. Yeah? So what was the quotient rule? Recall? So then quotient rule was low d high minus high d low over square below. Remember? So let's go ahead and do that. The negative, you can just think that it is negative one scalar multiple. So you can pull out in the front, and then you can just do low, we'll just copy, low, d high. We're taking derivative of x with respect to x, so it is just 1, minus high. My high is x, d low. Now you're taking derivative of y with respect to x. So I need the chain rule. Derivative of y is 1, but I need to multiply by dy dx over square below. So that will be y squared. you cannot have a dy dx inside of your second derivative function. So you need to replace your dy dx by negative x over y right there. Okay, so then this become negative y minus x times negative x over y squared, which is equal to negative y. This is plus now, and you have x squared over y squared. And you never leave a complex fraction answer, so you need to simplify that. So you can just multiply top and bottom of this quotient by y, since y is LCD. So let's go ahead and multiply everybody by y. So times y and times y. So then it will be, when you force to distribute, you get y squared. And when you distribute with this one, y's get canceled. So you get just x squared. And y squared times y in the bottom, it is y to the third. Now, that is the second derivative, but always pay attention. There is a way to simplify your answer. And in your answer, if you can simplify by original equation, you do. So actually, you could simplify this even more, since this equation, x squared plus y squared, is always 49. So you can write the answer as negative 49 over y to the third. And that is your second derivative. All right, good job, guys. This is everything in implicit differentiation, and I will see you in section 2.6.